All right, let's talk about one of the biggest tug of wars in software architecture, performance versus scalability. It's a classic challenge that can really trip you up no matter how experienced you are. So whether you're just starting out or you're managing a huge system, really getting the difference here is absolutely crucial. I mean, how many of us have been here? This quote just hits so close to home. You think, okay, I'm going to make this thing scale. You roll out this brilliant solution, and then you run it on your own machine, and suddenly it's slower than it was before. It's one of those, wait, what just happened moments that every developer has, and it perfectly sets the stage for what we're about to get into. So before we even think about writing code or throwing new servers at a problem, we have to stop and ask the most important question. What is the real problem here? When things feel slow, are we actually dealing with a performance issue or is it a scalability issue? Because trust me, they are not the same thing. And if you misdiagnose it, you're going to make things so much worse. Let's break down that diagnosis. A performance problem, that's pretty straightforward, right? Your system is just plain slow, even for one single user. Someone clicks a button, and they're waiting and waiting. A scalability problem, though, that's a bit sneakier. For one user, your system feels lightning fast, but the moment you put it under any kind of real load, it just completely grinds to a halt. One is about raw speed. The other is all about capacity. You've definitely heard this in a meeting. It's the ultimate trump card in any technical debate, right? Yeah, but that doesn't scale. What people are really saying when they use that phrase is that the very foundation of the system is hitting a wall. It's a huge red flag that you can't just keep patching things or adding more hardware. You've got to go back to the drawing board and rethink the entire design. Okay, to really wrap our heads around these ideas, we're going to step away from the keyboard for a minute. Let's make this less abstract and more concrete by heading to a place we all understand, the supermarket. This simple analogy is honestly a brilliant way to see the difference between performance, load, and all the different ways we can try to scale our systems. So let's set the scene. Our supermarket has one cashier, and this cashier is an absolute rock star. They can get one shopper completely checked out, paid, and on their way in exactly 1 minute flat. For any single shopper who walks up, the experience is awesome, fast, efficient. This is our baseline performance. And here is where it all starts to get interesting. The demand on our system just doubled. Instead of one shopper arriving per minute, which our cashier could handle perfectly, now 2 shoppers are showing up in that same 60-second window. The load has officially exceeded our capacity. So what happens next? Well, exactly what you'd expect. A line starts to form. The second shopper has to wait for the first one to finish, so their total experience suddenly takes 2 minutes. And while they're waiting, 2 more shoppers have shown up. The line just gets longer and longer. Now, notice, the cashier's individual performance hasn't changed at all. There's still a 1 minute per shopper machine. But the overall user experience, it's tanking. That right there is a scalability problem in a nutshell. Okay, so our supermarket's in real trouble. The customers are getting grumpy waiting in that line. How do we fix this? Well, let's explore 3 really common architectural solutions, but we'll keep it in the world of shopping carts and checkout lines. Our first idea is kind of clever. We notice some customers buy the exact same things every single day. So for them, we'll create a special pre-scanned receipt. Instead of scanning every item, the cashier just zaps this one receipt and boom, the whole transaction is done in 10 seconds. In the tech world, this is what we call caching, storing the result of a heavy calculation so you can just serve it up instantly next time. But there's always a catch, isn't there? What happens if that regular customer decides to buy a candy bar today? They hand over the special receipt, the cashier scans it, and error, it doesn't match. This is what we call a cache miss. So now the cashier has already wasted time trying the special receipt, and they still have to scan every single item one by one. The total time is now 1 minute and 10 seconds. It's actually slower than if we'd never tried our clever trick at all. Caching isn't a free lunch. All right, so that caching idea was a bit tricky. What's the most obvious, direct approach? Just throw more resources at it. If one cashier can handle 1 shopper a minute, let's open up 6 checkout lanes. 6 cashiers should be able to handle 6 shoppers a minute, right? This is horizontal scaling, just adding more servers to handle more requests. Simple. But as we all know from real life, this creates a whole new set of headaches. You inevitably pick the line that gets stuck behind someone with a million coupons, and you just have to watch in frustration as other lines fly by. Or what if a cashier's register breaks, or they just need to take a break? Their entire line becomes a single point of failure. everybody has to move. So just adding more resources doesn't magically solve everything.
So what's a better way? A more elegant solution? Instead of having a bunch of little, unpredictable lines, let's create one single, organized line that feeds all of the available cashiers. When you get to the front, you just go to the next cashier who becomes free. You've seen this at banks or modern grocery stores. And this is a perfect real-world analogy for a message queue.
And the benefits here are just so obvious. The whole system becomes fair and orderly. It's first come, first served. You never get stuck behind one super slow person because they're only occupying one of many cashiers. And the system is way more resilient. If one cashier has to step away, the line just keeps moving to the others. The overall flow of the system becomes predictable, efficient, and just better. Okay, we've had our fun at the supermarket. I hope that analogy helped make things click. Now, let's get back to our world and translate all of this directly into the technical terms we use as developers every single day. So let's just map this out one-to-one. The shopper trying to check out, that's a user request or background job hitting your system. The cashier doing the work, that's your server or your worker process. Adding more cashiers to handle more shoppers, that's classic horizontal scaling. And that beautiful, single, efficient line, that's your message queue, like RabbitMQ or SQS. See how perfectly it all lines up? And this brings us to the formal textbook definition of scalability. It all boils down to this one simple idea. A system is truly scalable if, when you add more resources, you get a proportional increase in performance. If you double your servers and your throughput only goes up by 10%, you don't have a scalable system. You have a system with a hidden bottleneck. Now, if these concepts are actually pretty straightforward when you look at them through an analogy, why is building truly scalable systems so incredibly hard in the real world? Why do so many projects get this wrong? This last part really gets to the core of what makes a software architect's job so challenging. And this right here is probably the most important takeaway of this whole thing. You simply cannot bolt on scalability at the end. It's not a feature you can just add in the last sprint. It has to be baked into the DNA of your system, considered with every single architectural choice you make right from day one. In the real world, the challenges are messy. First, you've got algorithmic complexity. An algorithm that's perfectly fine with 10 users might just fall over and die when it sees 10,000 because its cost explodes. Second, things change over time. As you add more servers over the years, you end up with a mix of old, slow machines and new, fast ones. A truly scalable system has to be smart enough to handle this mix without letting the oldest, slowest machine drag everyone else down. And that really brings us to the final question I want to leave you with. Take a hard look at your own projects, your own code, your own infrastructure. Ask yourself honestly, did we just build something that's fast for one user right now? Or did we actually architect a system that's ready to handle the success we're all hoping for tomorrow? Something to think about. Thanks for joining me.